Swayamprabha. Digital India. Educated India.
Greetings, and it's my pleasure to welcome you again to this course on CFD. We are now on to the week 8 of this course, and this is the last week for this course. So far we have learned different techniques in CFD, and in this week we are going to particularly see how some of these techniques are applied for a problem. So, in this week we will try to explain different discretization, convection and diffusion, pressure velocity coupling method, time integration procedure for a test problem, and we will also display corresponding code and how these are actually implemented in a working code. Now, for this purpose we take a test problem what is known as a lid driven cavity. So, we will first define the problem, then explain different numerical strategy to approach CFD to get a solution for this problem. We will do detailed procedure and explanation of every step and display corresponding code. Once you get solution, then we are interested to see the results in different form, and that stage of CFD is what is known as a post processing. In addition to primary variables in its form, we also have a derivatives of primary variables, and we will explain how to get different post processing using these primary variables and show the results. The problem considered is lid driven cavity, and it is shown here. What is shown here is a 2D cavity, it can be 3-dimensional also. So, in this we have depth and then width. Depending on the ratio of depth to width, it can become a square cavity or cavity of different aspect ratio. Now, all the 3 sides are wall, that is how it is represented as a hashed line. On the top you have a lid and it is driven by a velocity, and for this particular case u is equal to u, a specific velocity is given. Now, this can be one particular value or it can be a function of sine or cos. If it is a 2D, then it becomes square cavity. If it is 3D, it becomes 3-dimensional cubic cavity. Now, in this problem the geometry is very simple, as you can also understand from the figure. Once you have this driving velocity imposed on one side of the problem, then you have a primary vortex formed at the center and you have a corner vortex formed at these 2 corners. You can have a Dirichlet type of boundary condition, that is specifying a particular value for the variable. This is what is known as a Dirichlet condition. This we explained in the week 1 or week 2 lecture. So, in this figure Dirichlet boundary condition is in terms of velocity, as you can see here u equal to v equal to 0 on all the 3 sides of the wall. Then on the top you have a velocity driving condition u is equal to u and V is equal to 0. It is also possible to prescribe Neumann type of boundary condition for pressure. Depending on the Reynolds number, it may be a laminar flow or turbulent flow. As I mentioned in the beginning, you have a primary vortex formed and you have a vortex formed and these two corners. Now, depending on the Reynolds number, the primary vortex either stays at the center or it moves to one corner. Secondary vortices appear very near the bottom right and left corners. The intention of this week class is to completely understand the concepts of discretization, solving the Navier-Stokes equation, using a model problem of flow inside a lid driven cavity. As I explained in the previous slide, for this problem the top wall, in other words the lid of the cavity, is moving to the right with a specific uniform velocity and thus create flow inside the cavity as shown here. So, u equal to 1 meters per second is a specific velocity given and the lid is moving from left to right. We mentioned you can have a vorticity stream function formulation of the governing equation, or it is also possible to solve using primary variables. When you say primary variables, they are u, v, w and pressure. Because we consider two dimensional situation, we have only u and v and pressure is always there. For the sake of simplicity, we consider explicit Euler time integration. Because it is explicit, we learn the scheme is conditionally stable. Reynolds number we need to define and we need to have a length scale and velocity scale. The length scale in this problem is, it can be a side of the cavity or it can be aspect ratio of the cavity. In this particular problem, because we have considered square cavity, all the sides are equal. So, the side of the cavity can be a length scale and the top lid with the driven velocity is considered as a velocity scale. So, Reynolds number computed based on this length scale and velocity scale is 1. This is only for demonstration purpose. You can increase the Reynolds number and investigate the flow inside this problem. We have a diffusion term on the right side and convection term on the left side. So, diffusion term and convection term in Navier-Stokes equations are discretized explicitly. So, coefficient matrices are not formed for solving u as well as v momentum equations. Then we have a procedure called pressure velocity coupling. We learned 3-4 methods, that is Mach algorithm, simple, simple R, simple C and projection method. In this demonstration problem, we use what is known as a projection method to solve incompressible flow equation. We also learned what is projection method. However, for the sake of completeness, we repeat the steps involved in projection method. There are basically 3 steps. In the first step, we solve momentum equation without considering pressure term. So, in this problem, we are considering 2D situation. So, you have u momentum equation and v momentum equation. In u momentum equation, we have minus dou p by dou x. In the v momentum equation, we have minus dou p by dou y. So, in the projection method, we do not consider these pressure gradient terms and solve without considering. Hence, the obtained solution does not satisfy the divergence condition, that is del dot v equal to 0. Based on these velocities, we set up a Poisson equation for pressure, which is linked with continuity equation also. Hence, we get a Poisson equation. Once you solve the Poisson equation, then you get pressure field. Project this intermediate velocity onto the divergence free vector space using the pressure calculated above, and this pressure acts as a Lagrange multiplier and ensures continuity is satisfied. This is the important step in the projection method. Once you solve the momentum equation neglecting pressure terms, we get equation as shown here. So, we have a time derivative term as a first term on the left hand side, and then convection term as a second term on the left hand side. Then we have only diffusion term on the right hand side. We are not considering any other source term, hence the equation appears as simple as shown here. Pressure terms are neglected, only convection and diffusion terms are considered. Discretization is performed for convection term as well as diffusion terms at the nth time step, making the scheme explicit. So, the discretized equation for u momentum equation is shown here. All are evaluated at nth time level. New time level quantity to be determined is given by the superscript star. Because pressure is not considered, obtained velocity is a temporary velocity field, since we use superscript star. Now, to obtain the pressure Poisson equation, divergence of the momentum equation is considered, considering only the pressure terms. So, dou u by dou t equal to minus del p, and that implies u at n plus 1 level minus u star by delta t equal to minus del p. Take the divergence of the above equation to obtain equation what is known as a pressure Poisson equation. So, we do that step here as shown. So, we get minus del squared p on one side, and source term for the pressure Poisson equation is on the left side. Now, we can repeat all the steps for the second momentum equation, that is V momentum equation. Since the flow should be divergence free, but that is what the meaning of del dot V equal to 0. In other words, continuity is satisfied. At new time level n plus 1, we have to have the condition del dot u n plus 1 equal to 0. Now, using this condition, the above equation gets reduced to as shown here, minus del dot u star by delta t equal to del squared p, and this equation is what is known as the pressure Poisson equation. Using the pressure calculated in the previous step, that is, once you solve the pressure Poisson equation, you get pressure field everywhere. It is also worth getting remembered that Poisson equation or the Laplace equations are elliptic equation, and we need to have boundary condition prescribed on all the sides. Using the pressure calculated in the previous step, you can project the intermediate velocity u star on the divergence free vector space as shown here. So, u at n plus 1 level minus u star by delta t equal to minus del p, and u n plus 1 is a final corrected velocity equal to u star minus delta t and del p, and this is a important step in the projection method, and this is called projection step. Now, we have the test case problem, lid driven cavity. We defined the problem with the boundary conditions. We already mentioned the top wall or lid is moving to the right with the velocity of 1 meters per second, and if you are using velocity to prescribe boundary condition, then we have a Dirichlet boundary condition, or if you are using pressure, then you have a Neumann type of boundary condition. The cavity is a square with the dimensions 1 meter by 1 meter, and for both velocity as well as pressure type of boundary condition, there is a description given here. So, the first one is for velocity, as you can observe here, the Dirichlet boundary condition applied for velocity u equal to 0, v is equal to 0, and so on. Now, if you are using pressure to apply Neumann type of boundary condition, and that is what is shown here. So, dou p by dou x is 0 on these vertical faces, and dou p by dou y is equal to 0 on this horizontal face. We also learned about storage of variables. We have 3 possibilities. One is a collocated, staggered, and then semi staggered. We learned collocated method of storing the variable results in what is known as a checkered board problem, and there is a pressure oscillation. To avoid that, we have another method, what is known as a staggered way of storing the variables. In staggered scheme, we have a u velocity unknowns are located on the vertical faces, and v velocity nodes are located on the horizontal faces, and pressure is stored at the center of the cell. The grid runs from I is equal to 1 to I is equal to I max. You specify how many grids you require in x direction, how many grids you design in the y direction. This is a simple problem, hence we use a structured grid. We can use again uniform grid or non-uniform grid. In this problem, we define with the uniform grid. Staggering the u, v and pressure unknowns removes the pressure oscillation, which is the case in the case of collocated grid arrangement. Steps in simulating cavity flow: first we do grid generation, then discretize the governing equation, solve the momentum equation to obtain intermediate velocities u star v star, solve the pressure Poisson equation, project the intermediate velocity onto the divergence free space using the pressure calculated in the previous step, then repeat the process till the solution is converged. So, we have a convergence criteria defined. Based on that convergence criteria, you decide whether iteration needs to be stopped or to be continued. Once you get solution, then we are interested in post processing. Post processing of the results can be in many form. You can have a contours, you can have a lines, or you can go for the advanced post processing, stream function, vorticity contour, and so on. So, for the purpose of explanation, we take a simplified grid, structured uniform grid with the 4 by 4 grid points, that is 4 in the x direction, 4 grid points in the y direction. We define uniform grid in such a way delta x equal to delta y. 3 cells are created along x direction and 3 cells are created along y direction. The grid coordinates run from I is equal to 1 to I is equal to I max, j is equal to 1 to j is equal to j max along x and y direction respectively. And this is a grid arrangement shown here. So, I is in the x direction, j is in y direction. We define 4 grids in I direction. So, 1, 2, 3, 4. Similarly, 4 grids in y direction, 1, 2, 3, 4. So, 4 by 4 results in 3 cells in the respective directions. Okay. So, we have totally 9 cells. We are going to follow finite difference method of solving or discretizing the equation, and we also mention staggered grid is used to store variables. So, dx and dy are uniform because we define number of grids in x direction and y direction to be same, that is 4 by 4 in this case. We can find out what is dx and dy. So, this is the corresponding code that is used to generate grid. So, we have a command grid size and other parameters, I runs along x direction, j runs along y direction, RE is a Reynolds number, dx dy cell sizes along x and y direction, dt is a time step value, velocity is actually lead velocity. We have already defined I max to be 4, you can actually change it to any number. This is a number of, this is a grid size in x direction. Similarly, for the y direction j max equal to 4, this is a grid size in y direction, and this is required in later. I am now showing you actual working code written in MATLAB. So, what is shown here is the beginning of that code. So, some parameters needs to be defined in the beginning of the code, and this one such parameter is what is shown here as the iteration, that is given as number 20,000, and this is tolerance limit or convergence limit, that is error 1 10 to the power of minus 4, Reynolds number is 1, velocity is 1. So, in this particular slide we are interested to see how a grid is generated and what is the corresponding code available to generate a grid. So, we have compute parameters, then dx equal to 1 by I max minus 1 and dy equal to 1 by j max minus 1. We decide number of grid lines in that particular direction, that is given by I max and j max. Then the starting point for x, for grid in the x direction. So, x equal to 0, it goes to 1 and with the delta x that is defined as dx. Similarly, in the y direction it starts from y is equal to 0 and ends at 1, because we have defined the side of the square cavity as 1, and we have also explained dx equal to dy, that for simplicity we have considered dx equal to dy, and in this particular line we have y is equal to 0 dx, it can also be dy, and starting from y is equal to 0 to y is equal to 1.0. In this module 1 of this week, we have explained the test case problem, and then we have decided on discretization procedure, pressure velocity coupling, storing of variables, grid arrangement. Then I displayed the actual working code, how the grid is generated. In the next module, we will go to the next part of the algorithm, where we talk about discretization of convection term and diffusion term. Thank you.